Okay. Does this work? Okay. All right. All right. Thanks everyone.
It's only for recording. It's not for inclusion.
Oh, okay. Okay. Good. Thanks everyone for coming. So this talk is about on a topic in algorithmic game theory, and to be more precise, on mechanism design. So let me start with a definition of mechanism design. So what is mechanism design? It's basically algorithm design, but you have extra incentive constraints to take care of. And let me explain what I mean by that. So here's a way of thinking about an algorithm. So it's a box that takes in some input, produces an output, and maybe this output is something that's trying to solve an optimization problem. You're trying to maximize or minimize some objective. And there are, potentially some feasibility constraints you need to take care of in producing an output. Now, I want you to think about this running example for what a mechanism design problem might entail. So let's imagine that you have a bunch of resources that you'd like to allocate to some number of people interested in these resources, and we'll think of these people as being the customers. And let's say what you want to achieve is good utilization of your resources. So everyone has some value that they get out of using these resources. And one example of an objective you might have is to allocate resources to people that get more value from them. So this is like efficiency of allocation. You might have other objectives such as charging people money for their use of resources and getting the most revenue possible from this allocation. So here, the input to the algorithm now are these values that people assign to resources. The output is a possible allocation. Okay. Now, the challenge in this sort of a situation is that as the owner of resources, you have some objective that you want to achieve, but your customers might have a different objective. Every customer wants the most resources they can get as cheaply as possible. And by looking at how you map this input to the output, the customers might decide to lie about their true values and report something different so as to achieve an outcome that's better for themselves. Okay? So this is where the incentives of the participants in a system come into picture. So when we think about a mechanism, it's a system with many people participating, controlling information that they provide to the system in order to carry out this optimization. And the mechanism must take into account these sort of preferences and manipulation of input so as to be able to produce the right output. Okay, and so a mechanism is an algorithm that, in addition to whatever feasibility constraints you have in the system, also takes care of these incentive constraints. And what do the incentive constraints say? Well, they say that the mapping from this input to the output should be designed in such a way that every customer is happy revealing their true value to the system so that we can carry out the optimization correctly. Okay? If customers change their input, then we have no guarantee for how the optimization works out. So that's what we mean by incentive constraints. And the mechanism can achieve this by potentially changing how the input is mapped to the output. So instead of the optimal, we might want to do something different. And in addition, we sometimes allow the mechanism to compensate people or to charge people and use these payment transfers to modify the incentives of the participants. Okay. In addition, in some situations, yeah.
Reporting truthfully is sort of an inherently good goal.
So excellent question. So there's a principle in economics called the revelation principle, and what it says is, you could think of mechanisms where there's a different sort of solution concept where people do modify their inputs, but you can still figure out what they do in equilibrium, and it's still leads to a good outcome given those modifications. But you can basically ask people to reveal their inputs truthfully and then simulate this kind of strategization or manipulation yourself, and that simulation would give you the same outcome, but it would essentially mean that your mechanism now is incentivizing truthful reporting.
How robust is that transformation in the sense that this is a centralized thing, one shot or whatever?
That's right. So it's
all kinds of other interactions you could be in.
That's right. So it is. So as you pointed out, this makes complete sense in one-shot settings. There are settings where there's, through the protocol, there's some extra exchange of information going back and forth, maybe between the customers or between the seller and the customers. And in those settings, sometimes this doesn't apply. But for what we are going to talk about today, the information is only flowing in one direction from the customers to the seller, and so it's okay to talk. The revelation principle does apply, and it's okay to think about truthful mechanisms. And in fact, I'll come back to this issue, and one of the things we might desire from a mechanism is that it's easy for participants to be able to figure out how they want, what actions they want to take. And so truthfulness enables that, and in fact, it's necessary, but it might not be sufficient in guaranteeing that people know how to behave within the context of a mechanism. And sometimes this can be an extra goal that you can impose on your solution. Okay. So we'll come back to this a little bit later on. So in some settings, the mechanism design problem, because of the fact that there's this manipulation going on and the designer doesn't know the true inputs, this can turn out to be hard. And oftentimes an extra assumption that we make is that the designer of the mechanism has some extra information about the environment or the market that we are in. Think of this as telling us something about where the input is coming from, for instance, a distribution that generates the input. And so we're going to be working within this setup where the mechanism does in fact have this stochastic information about the input and can utilize that in figuring out how to map inputs to outputs. Okay. So formally, what does a mechanism design problem look like? So like I said, this is the basic optimization problem we are trying to solve, trying to maximize some objectives subject to some constraints. And incentive constraints here are going to look like the following. So here I'm imagining that there are n different people that are participating in this mechanism. Everyone has some input to report, and everyone is, any individual person is going to consider changing their input to something different. Okay. And let's say this U of I basically specifies the utility that this ith person gets from the output of the mechanism if their value were Vi, their true input were Vi. And what this person is going to do is they're going to instead consider reporting this V prime of I. And now if I put this together with whatever everyone else reports, and then the mechanism maps it to some other output, so X of everyone else's report and V prime of I, then this person with a value of Vi gets some different utility from that. And I want it to be the case that if they report the truth, then their utility is no smaller than what they would have gotten if they lied about what they have. Okay, so this is what an incentive constraint looks like. And here's the important thing to note about this. I'm going to have one such constraint for every possible report of other people and for every possible deviation of person I for every I. And so if you think about the number of constraints that the mechanism needs to satisfy, there are potentially exponentially many constraints owing to the fact that there are exponentially many different inputs to the problem, potentially. Okay? And so normally when we think about efficient computation or an efficient algorithm, we want it to be the case that we can solve this problem in time that's polynomial in the size of this input. And here we're talking about a single instance of the problem. But the incentive constraints are constraints that bring together all the possible different instances to the problem. Okay, and so the size of the problem blows up, but we still want to be able to solve it in time polynomial in the size of a single instance. Okay, so that's one manner in which mechanism design immediately becomes a little more challenging than what a standard algorithm for the same objective might look like. Okay. Okay, so before I go forward, let me just describe a few different settings where these kinds of problems come up. So you've probably all heard about sponsored search auctions or auctions for advertisers to place their ads on web pages. This is like the poster child for the econ and CS community. It's been one of the big applications, but there are a lot more. Some examples of things that there's been a lot of work on are spectrum auctions, kidney exchange, recommendation systems. There are some examples on which there hasn't been enough work and is something that the community is looking towards: routing on the internet, resource allocation in the cloud. In fact, there's a workshop going on this week at the Simons Institute in Berkeley about the practice of mechanism design and application areas, and these are among the many topics that have come up this week. So there are lots and lots of potential applications where incentives become important and computation becomes important, and so the connection of these two areas, economics on the one hand and theoretical computer science, is really pertinent and interesting. So this is a theory crowd mostly. So let me put on my AGT evangelist hat and say a few words about why you should care about mechanism design. So foremost reason, money, jobs. I'm only partly kidding, because if you're interested in money and jobs, you should probably be doing machine learning or networking or one of those areas. Okay. But more seriously, I want to say that mechanism design is very much up our alley for theory. It's basically just optimization within some sort of restricted computing paradigm. You have these extra constraints. Oftentimes these constraints have a nice structure, and I like to think about mechanism design problems as basically some sort of online problem. You're working within a computational system where there's some lack of information, and this is exactly the kind of thing that theoreticians, it's our regular kind of problems that we like to work with, and so it's very much in line with what theory can do and what theory likes to do. And it's also a great opportunity for us to export some algorithmic thinking towards economics, and we've seen some really good success on this in the last few years. Economists are starting to be more receptive towards concepts like approximation, competitive analysis, worst case analysis, and are being receptive to the value of thinking along these lines, and changing not just the solutions that they that we produce, but also some of the questions that some of the new questions that this line of thinking thinking generates in these areas. Yeah.
So maybe I'm getting ahead of myself, but do we know the UIs are fixed or can they change over time?
The UIs are fixed, and in fact,
they're given to us?
That's right. Yeah.
So one shot.
So I'm going to talk about, in fact, a dynamic setting, which is not a one-shot game. But the important thing is that so far, the theory has primarily considered a very specific kind of utility function, and I'll talk about that shortly. So going beyond that is definitely a nice sort of open direction to think about. So let me say a little bit about some of the main goals of mechanism design, and a very, very high level view of what we know and what we don't know. So, of course, from a computer science perspective, being able to solve these problems efficiently is goal number one, and when we can't, being able to approximate them well is an important goal. But a secondary goal, which is very important for practitioners and for economists, is structural understanding of the kind of solutions that standard mechanism design problems generate. So what does the optimal solution look like? Mechanisms that we see in practice, can we explain why they work well in practice or why they're so prevalent? So predictive or explanatory power is another very important goal. Another important consideration is that, as I mentioned earlier, oftentimes in these mechanism design settings, we assume that we know something about where the input comes from. Maybe there's a large market, and the people that are participating in your mechanism are some people drawn randomly from this market. This is a very standard assumption. And when we talk about optimal or near optimal mechanisms, often there's a worry about overfitting to the details of this model. And one important goal is to be able to come up with mechanisms that are not very finely tuned to the fine specifics of your assumptions, but are rather mechanisms that can work broadly. And so there are results of the sort that there's a mechanism that approximates the optimal one over a large class, let's say, of distributions. So you're shifting your worst case analysis from worst case over instances to worst case over some large class of distributions. And in economics literature, this sort of property is called detail freeness, and that's another important consideration. And likewise, robustness to modeling assumptions, such as what do the utility functions of people look like, etc. So these are all important things. And let me briefly mention sort of two broad techniques that have emerged in algorithmic mechanism design over the last 5 or 6 years. So one is a framework for optimizing problems for algorithmic approaches to mechanism design, and this is a very broad framework. What it basically shows is you can take a mechanism design problem and you can convert it into an algorithmic problem over a related objective. And in some cases, this gives us, if the algorithmic objective is easy enough, then this gives us a way of solving the mechanism design problem. So the good thing about this is it's a very broad framework. It basically gets us this first bullet point, not so much the other three. And there's a different framework that's arisen, and that is that we focus on some nice subclass of solutions that are simple, detail-free, robust in some ways, and then argue that this nice subclass contains near-optimal solutions, and you can find these near-optimal solutions efficiently. So this has some of the other good properties that I listed out, but on the other hand, this is currently not a broad enough framework, so we know positive results within this framework for very, very limited settings. Okay? Okay, so in terms of the kinds of settings that we know how to solve and those that we don't, we know computational solutions to problems that have small support. So the distribution from which the input is drawn is in some way small support. Doesn't mean that there are polynomially many instances, still exponentially many instances, but in some respects you can formalize the small support assumption. As I said, we also know simple analytic solutions for very limited class of problems through the second approach that I described. We don't understand simple analytic solutions for a broader class of problems. Sanjeev mentioned one-shot settings, and the framework that I described so far is sort of a one-shot framework, and we, for the most part, understand what we can do, what we can't do, or what we don't know how to do in one-shot settings. But on the other hand, online or dynamic settings are not well understood at all. The work in this direction is just about starting to happen, and this is a very wide open area right now.
How understood is that in economics? I mean, I've seen things like repeated games that's been around for a long time.
Yeah, so I'm going to focus on this for the rest of the talk, so I'll come to what's known and what's not. Yeah. Yeah, so there's a lot of work on repeated games. Here we're really talking about sort of like online mechanism design problems similar to online algorithm problems, where you have you're solving this, you're trying to solve this optimization for a system that's running over time or ongoing, and so it's different from a setting where you have the same game being played over and over again among the same participants. It's slightly different.
So what I meant was, have the economists studied that?
Yeah, so there's a lot of work in economics on this.
Similar to the regret framework? Or?
No, so this is very different. So this is like online optimization, basically.
But that's regret.
Yeah. Well, no.
Define it? Or?
Yes. So I'm going to define this formally very shortly. Yeah. And then one other quick direction that I think is very interesting is we understand settings where different participants are independent in the sense that there's no exchange of information between them. And another direction that's very nascent right now in computer science is informational dependencies among different participants. And I want to quickly say that mechanism design is an old subfield of economics. So all of these directions have seen a lot of work in economics, but this tends to be, very, there tend to be, positive results in very, very limited settings. And so a computer science treatment of any of these directions would be very fruitful and would really add to that literature. Okay, so for this talk, I'm going to focus on dynamic settings. So let me describe a very simple one-shot example that we will then extend to a dynamic setting. So here's what I want you to keep in mind. So we have a seller selling some item, and we have a buyer interested in this item. And here's how the mechanism would typically play out. So the buyer has a value that's drawn from some distribution. This is a known distribution. So the buyer draws this value, and then potentially reports, instead of his true value, some function of this value. We'll call it the bid of the buyer. And then the seller is going to take this bid and then map it to some allocation and also charge the buyer a price. Okay, and we'll think of the allocation as being basically the probability with which the buyer gets this item. So there's just a single item under sale, and this is just the probability that the buyer is going to get this item. Okay, and And then we're going to assume that the utility that the buyer gets from this outcome is the following. So, so V is the value that the buyer associates with this item. X of B is the probability that he wins the item. So this is the expected value that the buyer gets from getting this item. And then we just subtract the price that the buyer needs to pay. This kind of a utility function is called a quasi-linear utility function. It's linear in the payments, but this value can be something arbitrary. This is quite pervasive in mechanism design literature. The fact that it's linear makes it really nice to work with, and that explains why it's so pervasive. So what does the seller now want to do? So the seller faces the following constraint. So suppose the seller fixes these functions x and p. Now the buyer is going to try to maximize, is going to try to find a bid that maximizes this utility function. Okay? And the seller wants it to be the case that x and p are such that for every value v, this utility function is maximized when the bid is equal to the value. Okay, so that's the constraint. And let's say that we're talking about maximizing the seller's revenue. So the seller wants to maximize the expected payment and expectation over V drawn from this distribution that he gets from the seller. Okay, so this is the problem that the seller is trying to solve, and this is really well understood. Yeah.
What if the seller just says his objective is to maximize the revenue and drops this other constraint? Why does the seller care about this?
Okay, so so let's say that the seller didn't have to worry about this constraint, and let's say that the buyer was always truthful. Then what would the seller do if he wants to maximize the payment is to charge the seller whatever value he reports. So the buyer says, I want to pay $5 for this piece of fruit. The seller says, okay, give me $5. Now, but the buyer is then, if he was truly willing to pay the $5, knowing that the seller is going to charge him whatever he says, is going to shade his value a little bit, and would instead say, I'm going to pay $1 for this fruit. Okay, and so by ignoring this constraint, basically what would happen is that the buyer would not be truthfully reporting his value, and so therefore the seller would not really be making as much revenue as he thinks he might be making if the buyer were to report truthfully. Okay, and like I said, so the revelation principle, which I didn't really put on a slide here, basically says that if the buyer is going to strategize, then it's sufficient to consider mechanisms where the buyer's best strategy is to report his value truthfully, and so therefore that allows us to place this constraint.
So I always, I mean, there's a revelation principle which always confuses me too, but it always seems like, is there truthfulness so that we can do math with it? Because that's the input to the computation.
Right. So actually, you can, mathematically. So as long as you're working with some concept of equilibrium. So here, the concept of equilibrium is simple because there's only one person strategizing. So as long as you assume that this person is going to be maximizing their utility function, you don't have to restrict yourself to truthful mechanisms. And indeed, for this problem, so for instance, even if you have many buyers, there are many different kinds of auction formats known. For instance, the English auction, which is an ascending price auction, a Dutch auction, the second price auction, which is truthful. And it turns out that in this setting, all of them have the same expected revenue. That's a concept called revenue equivalence, because all of them have the same outcome at equilibrium. Okay, so essentially what's happening is that the second price auction is simulating the equilibrium of the English auction and the Dutch auction. And so that's basically the revelation principle played out. So it's sort of like a simulation. As long as you're at equilibrium, you could simulate that equilibrium rather than forcing the buyer to playing that equilibrium. So that's the idea, basically. Does that make sense a little bit? Okay. So dynamic settings. So now we are going to change the setup a little bit, and we are going to imagine that this buyer wants to buy a piece of fruit every day. Okay. So the first day, the buyer arrives and draws a value from some distribution, reports a bid as a function of that value. And then the seller picks some allocation and some price based on that bid. And then on the second day, the buyer comes back, but this time his value could depend on, is drawn from some distribution that could potentially depend on what his first day draw was, also potentially on what happened the first day. Did he actually get to enjoy the piece of fruit or not? And that could affect what his value for the second day is. And let's say that this F2 is known as long as you know what these arguments are. So we know all the parameters of the problem. And then, I'm sorry, that should be a B2. So the buyer reports a bid B2, and the seller picks an allocation and a price. The indices here are all broken, sorry about that. But these could again depend not just on the second day report, but also on the first day report. Okay? And then the third day comes around, and then the third day the buyer draws a value, and now this could be a function of everything that's happened in the past. And then the seller could pick an allocation and a payment that could be a function of everything that was reported to the seller in the past, and so on. Okay? Okay, so once again, we're going to assume that the seller's utility on day I is going to be the probability that he gets the piece of fruit times his value minus the payment that he makes. Okay? But this time around, when the buyer thinks about what bid to report on a particular day, let's say on this day 3, then he's not only going to think about how it affects his utility on that particular day, but also on what effect this could have on his utility on future days, because his bid today is going to potentially affect what the seller does on future days. Okay? And so the seller's IC constraint now is that on day I, if the buyer thinks about his utility today plus his expected utility in the future, then this entire thing is maximized by setting the bid equal to the value. Okay? Okay. And now once again, we want to maximize the seller's entire revenue summed over all the days, subject to this kind of IC constraint playing out every day. Okay, so I want to point out that this is quite a bit more complicated than what we had on the previous slide. So the buyer's decision for what to do on a particular day depends on the seller's functions for all the following days, affects the buyer's value distribution on all the following days. And the seller's optimization problem, on the other hand, should take these effects into account and then pick these xi, pi functions on every day. Okay, yeah.
So if it's much harder, let's say that the seller just wants to maximize his revenue on day I, is it much worse? Like, do you have a competitive analysis? Is it easy to show that it's much?
So just the day I, yes, then. Yeah, yeah. So then you can essentially solve this like a one-shot optimization problem. The idea is that you just want information up to then. You just want to think about this one-time interaction between the buyer and the seller, and this interaction could include all of what the buyer has learned up to then.
And
so.
How much worse is this approach to compare to this one? Can the seller do much better?
Oh, so you mean every day the seller, so the seller indeed cares about this total objective, but optimizes it 1 by 1 for every day.
Right.
Yeah, so that could actually be much worse. Yes.
So is this is an example of this the sale phenomenon? Like people don't want to buy clothes at full price and they wait for the sale?
Yeah, so that's sort of part of this, and one part of it is the ability of the seller to make a commitment. So here we are assuming that the seller can actually announce these functions ahead of time, and then that binds the seller into a commitment to actually use those functions.
Oh, I see.
Okay, so there are questions. Yeah, so one of the interesting issues that comes up there is whether or not the seller has an ability to make a commitment, and that can hugely change what you can do within the mechanism if the seller cannot make a commitment. So here we are assuming that the seller is able to make this commitment. Okay.
And
okay.
So for natural kind of, I mean, have you actually computed some numbers and see how much the optimum shifts, like for some reasonable?
Yes. So so even with 2 days, the optimum you can make it arbitrary. The gap arbitrarily back.
Well, I don't mean in theory, but like for reasonable choices.
Oh, for reasonable. Okay. So no, but the question. I'd have a hard time saying what's reasonable and what's not. Of course, it depends on what these distributions are. Yeah. But I'll shortly describe a very intriguing result where these are completely independent and you would still get a gap. So I'll do that. Before moving on, I want to quickly point out that there's an implicit assumption here, which is not always kosher, which is that you're assuming that the buyer is risk neutral. So the buyer is naturally facing some risk. His actions at the present moment affect what happens in the future in some stochastic manner. And so the different buyers may have different risk attitudes. One buyer may be willing to risk a little bit of a loss in order to get a high utility. Another one might not be willing to take any loss in the future.
So in terms of making that commitment, does it help the seller or the buyer?
It helps the seller hugely.
Okay, that's why they have Black Friday sales.
Yes, that's right. It helps the seller hugely. If the seller cannot commit, then the buyer becomes more cautious and can basically strategize extra.
Okay, so this explains Black Friday sales.
Yes. Okay, so what's known? So there's been this recent work in the CS literature on a special case of this problem where, in fact, so thinking about just the setting of 2 days, they assume that the distributions of values on the 2 days are completely independent. Okay, and then you might imagine that the seller should just treat every day individually. There's no correlation, but there is some exchange of information going on between the buyer and the seller, and it turns out that the seller can exploit that and do a lot better by taking into account what's going to happen on the second day to charge the buyer more on the first day and get a much higher revenue. So the thing I want to point out here is that even this setting where the two distributions are completely independent is highly non-trivial. And we only understand what the optimal thing to do is in very special cases. And so an example is, so in this paper by Papadimitrou et al., which is actually going to appear in Soda, they consider an example where what the seller can do is to charge extra on the first day for a commitment to sell to the buyer on the second day free of charge. So imagine that you have a, Apple says that if you're willing to buy, today's version of the iPhone, and then I'll, throw in the next version of the iPhone free of charge as long as you're willing to pay some extra amount. Now, if the buyer is uncertain about their value on the second day, but is risk neutral, then they're going to be willing to pay today, what their expected value on the second day is. And so in that case, the seller can, extract all of that expected value in revenue without, on the first day itself, whereas if the seller were going to wait until the second day, then the seller cannot quite extract as much, because then the buyer is going to be, is going to have this extra information that they can use to strategize. So that's roughly what happens.
So does that fit into the framework that you had before?
Yes. Yes, it does. So basically here, the seller, what the seller is going to do is to charge a little bit more. So if the seller were just thinking about day one, then for instance, the buyer reports some value, the seller cannot charge as much as the entire value because then the buyer would be shading their value. But then in this context, the seller can actually charge a lot more for the promise of selling the item for free on the next day, and can charge up to the buyer's value.
Where in that setting was their promise?
So the promise is here. So the seller can say that, well, the price P2 of B1, B2 is going to be 0 if B1 is such that the buyer is going to buy here. So for instance, this function could say that P2 is 0 if X1 is 1. Okay, if you buy today and pay me that extra amount, then P2 is going to be 0, and that's a commitment that I make. Okay, and also X2 is going to be 1 in that case. So the seller could actually make that commitment, and so thereby charge an extra amount here. Okay. I see that some of you are not happy with how the seller exploits the situation, and I'm going to, shortly make that same point that, when the buyer is risk averse, then you cannot, then the seller actually cannot use such strategies. And so, in some sense, that's sort of the reason that the kind of mechanism that these works come up with, you wouldn't actually expect to see in practice. This is not how Apple sells iPhones. They charge for one at a time, not, the commitment to give you the next one. But before that, let me just mention some more work on this. So like I said before, there's been a whole lot of work in economics on these dynamic settings, starting as far back as '84. And they've looked at all kinds of setups, values that evolve independently of consumption over time, value evolution that depends on whether or not the item was consumed, or maybe depends on some information that the seller possesses that the seller can think about whether or not to share with the buyers, and so on. So fairly general settings. And what these papers do is, under some fairly restrictive assumptions, they are able to characterize what the optimal mechanisms look like. But these are fairly strong assumptions. For instance, one of the papers makes the assumption that the initial value is in some sense independent of changes that happen in the future. All of these works make the assumption that the buyer is risk neutral, which is also the assumption that this work makes, which allows for this sort of a mechanism where you're charging for the future expected value before the buyer has learned that value. And the reason that these works make this risk neutrality assumption is because anything beyond that is mathematically really difficult to deal with. Okay. And most of these papers require the seller or the buyer to solve these complex MDPs. Even backwards induction doesn't work in many of these models for solving for the seller's best strategy. And the buyers as well, in thinking about how their current report affects their future utility, might have to solve a complex optimization problem. Okay, so this work is very far from what might ever be applicable in practice.
So, can I ask you a question?
Yeah.
So, in all this, one starts with this assumption that goods are goods.
Mm-hmm.
They're bread
Mm-hmm.
and so on. Except pretty soon, goods are not goods. Goods are,
what do you mean?
Goods are whatever you define them to be.
Yeah.
Right?
Okay.
And so, why do we assume that people know their utility function?
Okay, or why do we assume people know their values? Yeah. That's a good.
Why do we assume that
Yeah.
one of the things is not that
Yeah.
one of the games is not that people can get confused about their utility function.
Yeah.
In fact,
So
that should be on the table.
Right. So hold that thought. That's an excellent question. I want to come back to it towards the end of the talk. Okay. So let's definitely talk about that. And it's an important criticism.
I guess classically they talk about, I mean, even in my intro econ course we learned about this, that there's this theory of, like advertising and how you shift the demand curve, that sort of stuff.
Yeah. So, in many settings it's the case that, so in many settings it is the case that, values are not intrinsic somehow, but are derived from signals that the participants are getting from from the environment in some way. And there's some work on that, but it also, for any sort of mathematical treatment, you have to write down a specific model, and then you might question, is this model realistic or not? But one of the points that I might as well make right now and not towards the end of the talk is that in certain mechanisms, it might be possible for people to respond and pick an action without even explicitly knowing their value. And that's sort of one of the points that I want to make through the work that I'm describing. This is going to advocate a mechanism that's basically a pricing mechanism. You set prices on items, and even if people might not consciously know their value for an item, they can at least figure out whether or not they want to buy the item at a particular price. Okay, which is something that we do all the time, right? So I can't, explicitly place a dollar value on something, but I can react to a price and say whether or not I want to buy the item at that price. So there's some intrinsic value, let's say.
I don't see that it follows.
I'm sorry. It's, the fact that there's an intrinsic value.
Yeah, it doesn't follow, right? If basically you're saying that people can react and come up with an answer, but if they cannot figure out what the value is, maybe they are just reacting at random, and it doesn't correspond to a value for them because it's too hard to figure out.
Right. So all I'm saying is that if you assume that people have the ability to respond to prices, which I feel is a mild assumption because people respond to prices all the time, then you can define an intrinsic value based on that. There's a consistency assumption here that the responses are consistent, I think it's reasonable to think about how one might go even beyond that assumption, and that's a good question. Yeah.
Complicated for the reason
Yeah.
you say.
Right.
Yeah.
I think those may have been good assumptions 50 years ago, but it's not clear to me they're good assumptions today.
Yeah, we are slowly progressing, I think. So there's, much of the theory for a long time was based on very, very specific models, and now the community is starting to talk about robustness in various ways, and this is definitely, a direction for robustness against, these kinds of assumptions. Yeah. But I think, so one of the things that I'm advocating are pricing-based mechanisms as opposed to auctions that require far less from the buyers, in the decisions that they're making. Yeah. Okay. So moving on. So I'm not going to, do the general problem that I described. We're going to look at a very, simple special case of it, and I'll show you a solution for this simple special case. So imagine that what the seller is doing is selling an app on the App Store, and the buyer has some value for this app, and the way that this value changes over time is that you buy this app, you play with it, and then the next day, depending on your experience, your value changes by a little bit. Think of it as a random shock that's added to the value. And we're going to assume that the value stays bounded, and this is a process that continues forever until at some point the buyer loses interest in this particular app. Their value drops to 0, they stop buying, and from there onwards they never buy the app. Okay, so that's the setup that we're going to be working with. And the kind of properties that we want from the mechanism that we develop for this is, of course, we want to approximate the best possible thing for the revenue. But we also want this to be simple to compute and implement, simple for the buyer to respond to, and it's, in particular, we don't want to make any assumptions on how the buyer reacts to risk. Okay? We don't want to make the risk neutrality assumption. And so the question is, what can we do with that? Okay, so let me show you a mechanism and a particular sort of bound on revenue that is going to have those properties. So this mechanism is going to announce a sequence of prices. It's like saying the tth time that you want to play this particular app, you're going to pay a price of p sub t. Okay, so this is the sequence of prices. And now the buyer arrives and has this random value, and this value changes over time, and the buyer buys the app for as long as the value stays above the price that we announced. Okay? Now, a buyer that is risk neutral, so any buyer will keep buying the app until their value is above this, the price that is announced for that particular step. And some buyers may be willing to, go forward a few steps even if their value drops below the price. But we're just going to assume that the buyer stops buying at this point of time. And then the revenue that the pricing mechanism gets is the sum of the prices that we collected up to this point of time. Yeah.
So once the buyer stops buying, the buyer won't buy, can't buy.
Will never buy again. That's our assumption. Yeah. Okay. So because here we are imagining that the value evolves with use. Okay. So if the buyer stops using the product, then their value stops evolving, and then our price also stops evolving. There's no real concept of time here in the sense that, I might play a game today and then not play for the next 5 days and then play the game. So here, time is the specific uses of the app and not so much real time. Okay. So both the price and the value evolve by with each use of the app. Okay, so I'm going to call this the seller's risk robust revenue. If we announce these prices, any rational buyer should keep buying until this point of time, and then the seller should be able to make this revenue. Yeah.
So it seems like the buyer acts like a bit independently of the days. Like, is there any cumulative cost model for this? Like,
so here we are assuming there are no costs associated.
Oh.
So this is just a digital good that it costs nothing for the seller to allocate.
For the buyer.
Yeah. Oh, for the buyer.
Right. So like if I spend too much on this, then I'm done with the game over time.
Yeah. So we are. So this model doesn't take that into account.
Okay.
Yeah. Yeah.
Sorry, and a rational buyer might continue to purchase even after his value.
That's right. That's right, they might. We're not going to take that into account though. Yeah. How much time do I have? It's already 1.
Yeah, maybe a few more minutes.
Okay, maybe 5 minutes. Okay, so I'll try to be quick. Okay, so now the question is this any good? Okay, and let me say what we want to compete against. So here's what a different mechanism might do. If this mechanism knew where the value of the buyer started out, and suppose it knew how the value evolves, this mechanism could say on the first day itself, it could say to the buyer, well, I want to charge you your total expected value that you accumulate in the future, but then I'll give you unlimited access to the app. And if the buyer were risk neutral, then the buyer would accept this offer. Okay, and this is a mechanism that we want to be able to compete against. So going back to our picture here, the blue area is what this pricing mechanism gets in a risk robust manner. And if we were to allow the buyer's value to keep evolving until it went down to 0, then this red area is potentially what a different mechanism might get from the same buyer. And we want to come up with a pricing where the blue is some constant fraction of the red. That's our goal. Okay, so I want to claim that this is a pretty strong kind of guarantee if we can achieve it. So this pricing mechanism is really talking about the most averse kind of buyer, and the red area is talking about the most accepting kind of buyer, and yet we want the blue to approximate the red. Okay, so here's an example that shows that if you were to use a simple pricing where you always set the same price for every time period, then in fact you cannot get such a guarantee. And here I'm assuming that there's a fixed starting point and the value evolution is a simple random walk that's bounded between 0 and 1. And if you do a little bit of math, you can argue that the cumulative value is basically linear in the initial starting value. Okay, and I won't go over this. But if we pick a price of P, and the starting value is some V, then the amount of time that it takes the walk to get to this P is also about linear in the initial value. Okay, and you can do a standard random walk argument to get that. And so what ends up happening is that the revenue that the pricing would get would be P times this number of steps for which the random walk is alive. And this turns out to be quadratic in the initial value. And if the initial value is small, then this could be a large gap. Okay? And we don't want that. We want a small gap regardless of what the initial value is. Okay, so I'm speeding up a little because we're almost out of time. So the point of this work is to show that in fairly general settings, there's a simple modification of the pricing that I just showed you that gets a constant approximation. And this simple modification is that we charge a price of 0 for some number of steps. So this is like giving a free trial to the customer. And then we have a fixed price per step.
This used to be called the shareware model. 15 years ago, it was shareware.
Is that right? I should look up that term. I wasn't familiar with it. Okay, and where does it work? So this is a more general model of value evolution beyond the simple random walk that I showed you before. So this is a value that stays bounded between 0 and 1. It evolves as a martingale, but in fact the random shock at every step could depend on the entire history of the value. So you're playing the game, you unlock a new feature, or depending on what your experience was in the past, you could have this random shock, but it's always an expectation 0 shock. And we also assume that the step size of this walk is bounded, and then there's some minimum randomness at every step. And if we have all these properties, then it turns out that this sort of pricing is going to get a constant fraction of the buyer's cumulative value, where this fraction depends on the ratio of the upper and lower bound on how much randomness we are adding in the walk in this value evolution at every step. Okay.
So delta is.
So delta is saying that there's some, it's the variance, yeah, it's the square root of the variance at every step. So delta and epsilon are comparable. If you had a standard random walk where the step size is the same every time, then the delta and epsilon would be exactly the same. Here we are allowing for the delta and epsilon to be different, and in particular the walk could sometimes be fast, sometimes be slow, and that could depend on the entire history of the walk. So C is the price that, so it's like we give a free trial up to T steps, and then the price is, oh, how large is C? It's going to be some constant that depends on delta and epsilon.
So delta is always smaller than epsilon?
Delta is smaller than epsilon, yes, because epsilon is the upper bound, delta is the lower bound. Okay, the conditions are slightly different, but essentially delta is a lower bound on the size of the step, and epsilon is an upper bound on the size of the step. Yeah. Okay, and basically the way we analyze this is to say that, well, there's going to be some probability that the walk is going to become, the value is going to become very high. And if this event happens quickly enough, namely before our free trial ends, then the walk stays alive for a long time, and we get to exploit the revenue. We get to charge the buyer some amount. And with some probability, the walk is quickly going to go down to 0, but that's fine. Okay? And the key thing here is to make a good choice for the length of this free trial period, so that there's both a good probability that the walk is going to climb up before the free trial ends, and and T is not too large, so that we still have some time before the walk hits C. Okay, so we need to balance both of those, and we show how to balance both of those. And I'm not going to go into the proof, so let me quickly skip these, but I'll be happy to share details if anyone's interested. I think it's a neat argument. So that's basically the theorem that we have. So I'm just going to conclude. So the point of this work is to consider dynamic settings, where if you were to try to solve the problem, try to write down a mathematical description of the problem, you'd have to make assumptions on the buyer's attitude towards risk, on the specifics of the value evolution process. And we want to get around all of those artifacts of the model by looking at a simple class of mechanisms and looking at a simple sort of target to compete against, namely the buyer's cumulative value. And we show that under some assumptions this can be done, and it gives us a reasonable approximation without knowing too many details of the model. And of course, the approximation factor is somewhat large. It's this epsilon over delta cubed. If that ratio is large, then the approximation factor is large. And part of that is, just an artifact of the way we set the prices and the way we analyze it. And you might ask, well, what if I were to use some more details of the process? So here I'm using very little knowledge about the process. What if I were to use more? Can I do better? And I think an interesting sort of class of questions that this kind of result generates is just asking about how well we can do if we were to optimize over this special class of mechanisms. Okay, so I don't want to optimize over all possible mechanisms, but just over this very special class of mechanisms. And then we might be able to do a lot better. And this sort of question makes sense in many of these settings where the optimal solution turns out to be complicated. We would like to weaken assumptions that we make and also extend it to other dynamic settings. So this was a very, very special case of a dynamic mechanism design problem. So that's it. Questions? Yeah.
How important is having the allocation parameter? Because I imagine in real life, most people won't be happy with paying money and then having some chance of not getting it.
Okay, so a very good question. So this is, in some sense, a question about randomized mechanisms versus deterministic mechanisms. People don't like randomness so much. And indeed, it's the case that optimal mechanisms tend to be randomized, and there are results of the form, within one-shot settings, there are results of the form that the benefit of randomness in some cases is small, and in other cases is large. So, so I think, again, this sort of question makes sense where you ask, well, what if we tried to optimize over the class of deterministic mechanisms where there's no randomness in allocation, and because of sort of an integrality issue, oftentimes that is harder than to optimize overall randomized mechanisms. And it's also known that in some cases the gap is huge. So there are trade-offs, but it's a good question, and it's the kind of question that comes up a lot of work on that.
So in the mechanism you just the C and T depends on the parameter?
They depend on epsilon and delta, but not on other details.
So what if the seller doesn't know this in advance?
Yeah, that's a good question. So one of the things that the seller could do is to, so in many of these mechanism design settings, the mechanism, the parameters in the mechanism depend on the distribution that is generating the input. And mechanisms that have few parameters to tune can typically, sort of be learned. So you can think of a machine learning framework where you're trying to tune these parameters. And there's a rough correspondence between how many parameters you have to tune and how many sort of samples you need to be able to learn those parameters. I haven't thought about that within this dynamic context where you'd actually have to observe the value evolution to say something about it, but you could imagine that if there are lots and lots of buyers and somehow you can see this value evolution process, you could ask how many buyers do you need to observe before you can figure out which C and T work well over the class of all C and T pairs. Other questions? Okay, thanks.
Shuchi's around, the rest of the office, if people want to please. At least one group is signed up, but others won't be.
Okay.